Welcome to week 12. This week we are going to wrap up Markov chain Monte Carlo methods. To recap, last time we introduced the Metropolis-Hastings algorithm, which is a very flexible and general method that can be used to construct a Markov chain. To recap, Bayesian inference relies on the posterior distribution of the parameter theta given the observed data x. The idea behind MCMC is that we want to construct a Markov chain for thetas with the posterior distribution of theta given x as its stationary distribution. For the Metropolis-Hastings sampling algorithm, at each iteration, we will first generate a y given the last theta t from the proposal distribution gy given theta t. And then the sample y will be accepted with the probability given over here. If we decide to accept, then the next sample of theta will be equal to y. Otherwise, the next sample of theta will be equal to the last sample of theta. We also introduced a special case for the MH algorithm, which is called the Metropolis algorithm. This is the case where we use a proposal distribution G that is symmetric around y and theta t. In other words, G of theta t given y will be equal to G of y given theta t. And in this acceptance probability, these two G's will cancel out and we're left with the ratio of the two F's. Once we get the samples of theta, obtained using MCMC, for example, using the Metropolis-Hastings algorithm, then after tossing away the burn-in, which are the initial iterations where we believe that the chain has not yet converged, well, after tossing them, then we can use the post-burn-in iterations to approximate the posterior distribution of theta. We can also construct various sorts of point estimates, such as the EAP, which is the posterior mean. In this week's lectures, we will cover a few topics and wrap up MCMC. First thing we will introduce is the independent sampler, which is another special case of the MH algorithm. And then we will go into the multidimensional world where our unknown parameter is not a single scalar, but a vector. Here we'll introduce the Gibbs sampler, which is particularly useful when theta is a vector. In other words, we have multiple unknown parameters. Following by that, we will introduce some methods for monitoring the chain convergence. So one question we mentioned last time is how do we determine when has the chains converged to the stationary distribution? So how should one determine the length of the burn-in cycle? Well, this time we will introduce some statistical methods and convergence diagnostic statistics that can be applied.